Welcome to EK307 Electric Circuits. The purpose of this lab preview is to introduce you to microcontrollers and to give you some tips and hints about how to approach the experiments. Why are microcontrollers part of EK307, you might ask? Isn't this course about circuits? The answer to your question is that microcontrollers make the world work. These little chips can be found in many different sizes and forms in just about everything you can imagine. All these things have microcontrollers in them. As I said, microcontrollers make the world work, whether we see them or not. What does this lab do? This lab helps you to understand the digital world of ones and zeros, how numbers can represent binary bits, how a microcontroller makes decisions, how microcontrollers are programmed. Here's what this lab does not do. It does not make you an expert C or C++ programmer. It doesn't replace a course on microcontrollers, and it doesn't teach you every last little thing about microcontrollers. Here are some of the key concepts to keep in mind for this lab. The purpose of this lab is to help you learn what goes on inside a microcontroller, how the world of software interfaces with the world of hardware, the function of an input-output port, and the role of a software time delay. Finally, the meaning of duty cycle. A bit of practical knowledge. Your microcontroller will come installed on the development board. More about that in a little while. You can connect the pins of your microcontroller directly to your breadboard. The pins of the microcontroller are presented in sets of 8 called ports. And in the lab kit that you purchased for this course, you will find a set of rainbow jumpers that you can use to make connections between the microcontroller board and the breadboard. If convenient, you can also use the regular jumper wires from your kit as well. Most of you will use the MSP430 launchpad to do this experiment, to do the lab experiments. The actual microcontroller chip is located in the center of the board. Most of the board serves as a development system that allows you to program the microcontroller and interface with its ports. The MSP430 has 2 ports. Port 1, consisting of the pins P1.0 through P1.7, are located on the pins shown. Port 2 consists of pins 2.0 through 2.7. This schematic diagram will also help you identify where the ports are on your MSP430 microcontroller chip. The red rectangles indicate the locations of the port 1 pins, and the blue rectangles the location of the port 2 pins.
Some of you may already be familiar with the Arduino Uno board. If so, feel free to use it instead of the MSP430 to do the experiments in this lab. The Arduino has one digital input-output port consisting of 14 pins, 0 through 13. It also has an easily identifiable analog input port. Now something about binary numbers. Binary numbers stand as a contrast to the analog numbers with which we have become familiar thus far in the course. The analog world interfaces with the digital world through a process called analog to digital conversion. Similarly, the digital world interfaces with the analog world via a process called digital to analog conversion. Let's talk about how signals are represented in the digital world. The binary or base 2 digits 1 and 0 are represented by voltage levels. A voltage level of 3.3 volts, or 5 volts on the Arduino board, is used to represent the binary digit 1, sometimes called a high state. A voltage source that has been set to 0 is used to represent the binary digit 0, sometimes called the low state. Numbers in a microcontroller are stored in groups of 8 digits, or bits. Each bit can be set to a 1 or a 0. Each of the bits in a word has a bit position, and each bit position carries a weight that increases from right to left. These numbers are stored inside the microcontroller. The bit position indicates the decimal weight represented by the bit. The bit on the left, carrying a weight of 128, is called the most significant bit, or MSB. The bit on the right, called the LSB, or least significant bit, carries a decimal weight of just 1. Here's an example of how the binary word can be used to represent a decimal number. Let's suppose that the number shown here, 10001001, represents the variable x inside a microcontroller program. Well, the 1 in bit place 128 contributes 128 to the total that will comprise the variable x. The next 3 bit positions are 0, so they don't contribute anything. The next bit position contributes a total of 8, the number 8 to the total comprising x. And finally, the LSB contributes a 1. If we add up all the contributions of the bits that are set to 1 in this example, we get 137. So the binary word shown in the middle of the slide equals 137, represented as a decimal number. There are a number of operations that can be performed at the bit level. These operations should be covered in lecture, but briefly, the AND operator has at least 2 inputs, and the output is set to 1 only when both inputs are equal to 1. The NOT AND operation produces an output that is the negative of the AND operation. In this case, when both inputs are 1, the output is a 0, because that is the inverse of the 1 produced by the AND operation. The NOT operator is very simple. The output is equal to the inverse of the input. Other operations performed at the bit level include the OR operation, the NOT OR operation, and the exclusive OR operation. In the exclusive OR operation, the output is equal to 1 or high only when either one of the inputs is 1. If both of the inputs is 1, the output is set to 0. Let's talk about port directions. The pins of a port in either of the microcontrollers used in this experiment can be set to receive signals or send out signals. In the case of the MSP430, a command in the program called the dir command is used to set the direction of the pins of the port on a pin-by-pin basis. The example that we will use in this tutorial is the command p1 direction equals 0. That means setting a register inside the microcontroller with all its bits equal to 0. That register determines the directionality of each of the pins in port 1. In this case, 0 indicates that all of the pins are designated as inputs. Data will come in from the outside world and be used, read in by the microcontroller program and used to do something. Similarly, let's suppose that we include a command P2 directionality equals 255. Remember that 255 is obtained by setting all the bits in a word to 1. In this case, the word in question is a register inside the microcontroller that it reads to determine the directionality of the port pins. So setting P2 dir to 255 with a 1 in every bit position designates each of the bits of port 2 as outputs. Data will be produced by the microcontroller and sent to the outside world. Now, the EK307 website includes some starter code to help you begin the programming exercise. We won't go over all the details of the program, but we'll highlight some of the features here in this tutorial. You must always have an include statement in your program. This statement reads from the library in the Code Composer Studio all of the various auxiliary files that are required for the microcontroller to work. You don't have to worry about what those files are. You just have to have this include statement at the very beginning of your program. I should mention, if I forgot before, that a double slash line at the beginning of a program statement or any section of a program statement indicates that everything to follow is simply a comment line and not executable code. You must declare every variable you intend to use ahead of time when you program the MSP430. In this lab exercise, we will typically only use integer variables. So here, the integers n and k are declared for future use without being set to a particular value. They'll have to be set later in the program. The variable t is preset to the value 0. That means we can start using t right away in our program code. We can also change it later on if necessary. Note that variables are case dependent in the C programming language of the MSP microcontroller. This next statement sets all of the pins of port 1 to be outputs, as previously discussed. And again, the number 255 goes into some register inside the microcontroller, and the microcontroller uses that register to determine the status of the pins of port 1. This next statement sets all of the pins of port 2 to be inputs. Again, the number 0 goes into a different register inside the microcontroller. This statement, P1out equals 1, recognizes that port 1 is set to be used for outputs, and it sets pin P1.0 high, while all other port pins low. If we were to represent the port pins as a word, you can see that every pin is set to 0 or the low state, except for pin 1, which in this case would register 3.3 volts. All other pins would register 0 volts. Remember, these are actual port pins that appear on the microcontroller development board. Alternatively, if you take the microcontroller out of the development board, on the actual pins of the microcontroller chip. In this next example, port 1 is set to the value 128. That means that only the 128-bit place is set high. All other bits are set low, so the pin corresponding to the MSB of port 1, P1.7, will be high. All other port pins will be low. Another statement can be used to read data into the microcontroller. Up above, we declared a variable n. In this statement down below, we have set n to the binary digits represented from the outside world, or imposed by the outside world on port 2. Remember, in order to do that, you actually have to have voltages applied from either a circuit or another microcontroller or some other digital circuit. So let's suppose in this case that the port 2 pins were set with the LSB high and the fourth bit from the right set high. That would represent the number 9 in decimal, and inside the executing program, the variable n would be set to the number 9. The variable capital T has special meaning in the MSP microcontroller, and it pertains to these statements that we simply ask you to cut and paste into the program, or leave them intact if you use the starter code program. The variable that we have to worry about is the capital T. In this case, we've declared T to be a 0, so it's automatically read as such by these statements. What these statements do is to set an internal timer inside the microcontroller. The value of T can be set to a number between 0 and 3, representing different values of time delay. Now in the starter code, you have a section that's called the interrupt void watchdog timer code, and we've structured the starter code in this very simple way because it's easy to get started writing programs without much programming experience. If you cut and paste all of the code shown in the starter code verbatim into your program, and then simply put your execution code inside the interrupt void section of the code, it will be executed every capital T milliseconds or microsecond. In this case, T is set to 0, so every time 33 milliseconds goes by, the program will execute what you've put in between these curly brackets once every 33 milliseconds. Now let's talk about the actual experiments. Project 1 Part A asks you to apply a number to port 2, set up as an input, and then apply the output to LEDs connected to port 1. So the thing you have to do in this experiment is set up all port 1 pins as outputs and set up all port 2 pins as inputs. And then read a 3-digit number into port 2. Now of course you will have to design an external circuit that can apply either 0 or 3.3 volts to the port 2 pins, depending on whether you want those individual pins to be high or low. The fact that you're asked to input or to set only 3 pins of port 2 means that we're asking for a number between 0 and 7. The number 0 in binary is 000, and the number 7 is 111. After that, you should write a program that will tell the microcontroller which of the port 1 pins to set high, and every pin set high will light an LED. And you should arrange the program so that the number of LEDs that are illuminated is proportional to the number you've read into port 2. In other words, the higher the number read into port 2, the larger the number of LEDs in a row should be illuminated. If you think about this operation, it is in essence creating a bar graph that reads a number into 3 pins of port 2 and produces a bar graph indicating the strength of the number that's applied to the port. So project 1 Part B, you have to proceed carefully because it asks you to apply voltage externally to the microcontroller. Now note that for all other experiments in this lab, the microcontroller board is powered by way of the USB cable connected to the computer. If you choose to do Part B of Project 1, you must disconnect the USB cable from the microcontroller after you have downloaded your program. So you disconnect the cable right here at the USB cable interface. The experiment then asks you to set a voltage source to 3.3 volts and connect it to the microcontroller, VCC, and ground pins to apply 3.3 volts externally to the microcontroller. Remember, this connection is for Project 1 Part B only. The lab assignment then asks you to measure the current required by the microcontroller as a function of the number of illuminated LEDs. Now, how are you going to measure that current? Well, you'll need to set up the multimeter to be an ammeter. You do that by pressing the DCI button on the control panel. And remember, you have to press the function button or the shift button while you press this DC button to make it correspond to current. And then you have to connect the ammeter in series with the voltage source. So you do that by taking a wire and going from the plus side of the 3.3 volts to the plus side of the I input of the meter. And the current will go through the circuitry inside the meter, come out the low side, and then that low side provides current to the microcontroller board. In this way, you can measure the amount of current that is passing through the ammeter into the microcontroller board. And by knowing that current and the voltage being used to supply it, you can determine the power required by the microcontroller. Project 2, Part A, asks you to create a circuit that changes the speed of a DC motor. The little circle in the circuit schematic represents an actual physical motor, which you can sign out from the instrument window in the EK307 lab. The idea of this lab is that the motor speed will be determined by the average of the voltage that's applied to its terminals. Now, because the motor responds relatively slowly, we can apply a set of pulses that have an average DC value. If the pulses are fast enough, the motor will interpret that signal by way of the average DC value that is applied. For example, if the duty cycle, defined as the percentage of time that the waveform is high, is 50%, then the average value will be half of the peak value. The voltage spends half of its time in the high state and half of its time at zero. On the other hand, if the duty cycle or percentage of time that the waveform is high is only 25%, then the average value of the entire signal will be just 25% of the peak value. The voltage is high or on 1/4 of the time and down 3/4 of the time. The motor is turned on and off by way of this little device here called a transistor. Now, transistor is a fairly complicated device. You'll learn all about it if you take EC 410 electronics. In EK307, we're simply going to treat the transistor as a simple electronic controlled switch. If 0 volts is applied between the left-hand side of this current limiting resistor and the right-hand terminal of the transistor called the emitter, then the switch is off, no current flows through the motor circuit, and the motor does not turn. Conversely, if a voltage is applied to the two terminals of the transistor switch, then it's as if the switch is closed in the motor circuit, current can then flow, and the motor will rotate. And again, the speed of rotation will be proportional to the average DC voltage applied to the switch. Here's what you will need for Project 2, Part A. You will need a motor driver circuit connected to a port pin. You will need a timing loop in software inside the microcontroller. You'll need some sort of algorithm to determine the percentage of on time versus off time. In other words, some way to set the duty cycle. For Project 3, Part A, here's what you will need for this experiment. You will also need a timing loop inside the microcontroller, an LED driven by an output pin, and an algorithm to determine when to light the LED. Note in general that either of the microcontroller boards, the MSP or the Arduino, is incapable of driving an LED directly. It would require too much current be supplied by the microcontroller. So it's important to always put a current limiting resistor of 500 ohms or a kiloohm between the port pin producing the voltage and the actual LED, which is connected from that pin to ground. The algorithm will determine when to light the LED. Now, this exercise asks you to represent letters in Morse code by the way the LED blinks. Now, a good way to do that is to simply declare a fixed amount of time that is 1/3 the duration of a dash in Morse code, and that is equal to the duration of a dot. And then you can have that timing loop just go on continuously and have an algorithm to determine whether during that loop the port pin should be set high or low to represent the Morse code of the letter in question. Here, the letter B is represented in Morse code by a dash and 3 dots. So here you see that this time interval is set to on for the dash, off for the dead space, on for the dot, off for the dead space, on for the dot, off for the dead space, and on for the last dot. For Project 3 Part B, you will need 2 timing loops inside the microcontroller, one for the audio signal and one to time the dots and dashes. You will also need a driver circuit connected to a loudspeaker for Part B. You can use the same circuit that we discussed for the motor controller, but instead of connecting the motor between VCC and the transistor, you can connect the loudspeaker from your parts kit. You'll also again need an algorithm to determine the percentage of up versus down time, the duty cycle corresponding to the Morse code of the letter you wish to reproduce. So once again, let's suppose that we want to represent the letter B. As before, in the case of simply illuminating the LED, we need time intervals that represent the dash, the dead space, and the dots. But we also need a faster timing loop to produce the audio signal that will be used to energize the loudspeaker during the times that a dot or dash is present. We recommend that you produce an audio tone in the range 500 Hz to 1 kHz because it's easy to hear and not annoying to your neighbors. One final note, and this is optional for all of the experiments, but a good thing to know if you decide to experiment further with your microcontroller. The purpose of the Launchpad board, the red board, or the blue board in the case of the Arduino, is to give you an environment in which you can interface the microcontroller to the computer via the USB cable, and also provide some diagnostics as to what's going on inside the chip. After you've perfected your program and downloaded it into the chip, you can always pry the chip up carefully and install it right on the breadboard and use it without the development board to run circuits or whatever else you're having it do. In the case of the MSP430, you must make one special connection to allow the microcontroller to work. First of all, of course, you have to connect 3.3 volts from the power supply pin VCC to ground, and you have to connect ground pin to ground. The reset pin is something that resets the program of the microcontroller when it is set low. So to keep the program running all the time, you have to connect the reset pin to the VCC pin via a resistor, typically 10K in value, although the value is not critical. Okay, that's it. As always, remember 2 things as you are performing the lab experiments. The first is to learn lots, and the second is to have fun.